Hey programmers! So today I want to talk about a data structure and it's the graph data structure. So a graph data structure in programming looks something like this. It's a set of nodes connected by edges. So this is an example. This is a very basic example of a graph. And here I'm going to draw 4 nodes connected by 4 edges. And these nodes can have values associated to them. So for now I'm going to call them node 1, node 2, node 3 and node 4, and these are called edges between the nodes. So this is an edge, this is an edge, this is an edge, and this is also an edge. So edges just connect two different nodes. So a graph can be more complicated than this. For example, it can have loops such as this. So a loop is basically a node connected to itself. So a loop from 1 to 1 would be just something like this. Or it could also have multiple edges, which would look something like this. There are different ways we can classify the graph. One way to classify a graph is based on whether it is directed or an undirected graph. So this is an example of an undirected graph. And the difference is that in an undirected graph, these edges don't actually point to a node. So all these edges don't actually point to any other node. And they're not from any node to another node. So in a directed graph, every single edge would point to a node, such as this. So this particular edge would point from node 1 to node 2, this edge could point from node 3 to node 2, and this edge could point from node 4 to node 3, and this one from node 1 to node 4. And this is purely arbitrary. It could also happen something like this or something like this. Another way to classify a graph is on the basis of weights. So in a weighted graph, so this is an example of a non-weighted graph. In a weighted graph, every single one of these edges would actually have a weight. So for example, it could be something like this. So what this means is that this particular path from node 1 to node 2 or from node 2 to node 1 will incur a cost of 3. Hang on, let me just draw that better. Okay, so this will incur a cost of 3 and this particular path will incur a cost of 2. Let's suppose you need to move from node 1 to node 3. So this is your start node and this is your end node. So here there are two paths that you can take. You can go from node 1 to node 4 and then to node 3, or you can also move from node 1 to node 2 to node 3. Okay, but the difference between these paths, although when using both of them you will actually only come across two edges, the difference lies in the weights of these edges. So you want to take the path with the minimum weight. So the total cost incurred by a particular path such as 143 or 123 is the sum of all the weights of all the edges in the path. So for 1, 4 and 3 we are going to cross this edge and then this edge. So the cost that we incur is 5 plus 1, which is equal to 6. The cost that we incur is equal to 5 plus 1, which is equal to 6. If we had taken the other path 1, 2, 3, the cost, so firstly we'll cross this edge which has a weight of 3 and then this which has a weight of 2. So the cost is going to be 3 plus 2. The term weight and cost is used interchangeably and it means the same thing, so you can use anything you like. So the weight here is, so the total cost or total weight of taking the path 1, 2, 3 is 5, whereas the total cost or weight of taking the path 1, 4, 3 is 6. And we need to minimize the total cost. So we will take this path. This path is more optimal, or this path is the optimal path in this particular example. Hang on, let me just get all this out of the way and we can continue. Okay. So now I want to discuss the simplest of all graphs, which is the undirected and unweighted graph, such as this. So this is going to be a trivial example that we are going to use for the entirety of this video, and later I'll come to more and later I'll talk about directed graphs and weighted graphs and how we can represent them or implement them in our code. But for now, let's focus on this graph. So an important question is, how can we represent this graph in programming? And now there are multiple ways to do this. One of those ways is something called an adjacency matrix. Okay, so an adjacency matrix is nothing but a matrix of order n. So it's an n by n matrix. It's a square matrix if n is the number of nodes in this graph. So here n is equal to 4. Okay, so I'm going to define the element aij of the adjacency matrix. So what aij simply represents is the element in the ith row and jth column of the adjacency matrix. So aij is going to be 1 if ith node and jth node are connected to each other via an edge, and 0 otherwise. This will become a lot clearer with the help of an example. So I'm going to use this graph as the example. I'm going to draw the adjacency matrix over here. Okay, so remember aij is equal to 1 if the ith node and the jth node are connected via an edge. So here what we're thinking about is, so the value here is going to be 1 or 0 depending on whether the first node is connected to the first node. So this, remember, this is I, the rows are represented by the I, and this is J. Okay, so these are the columns that are represented by J. Okay, so remember the graph can also have loops, something like this. So node 1 can be connected to itself, but here in this example node 1 is not connected to itself, so the value here is 0. Is node 1 connected to node 2? And we see that there is a connection over there. And we see that there is a connection over here, this particular one. So node 1 is connected to node 2, so the value here is 1. Is node 1 connected to node 3? No, node 1 is not connected to node 3. So the value here is 0. Is node 1 connected to node 4? And yes, there is an edge right over here, and node 1 is connected to node 4, so the value here is 1. And we can use this to fill out the rest of this adjacency matrix. So node 2 is connected to node 1, node 2 is not connected to itself, node 2 is connected to node 3, and node 2 is not connected to node 4. There's a 0 over here. Node 3 is not connected to node 1, sorry. It is connected to node 2. It is not connected to itself, but it is connected to node 4, so there's a 1 over here. Node 4 is connected to node 1, there's a 1 over here. Node 4 is not connected to node 2. Node 4 is connected to node 3, and node 4 is not connected to itself. There's a 0 over here. So this is our adjacency matrix for this particular graph. And there's something interesting to note about this matrix. So I'd suggest that you pause the video and try to figure it out. So now that you're back, I'm going to explain what's the interesting thing about this matrix. You can see that this particular matrix is actually symmetric. What that means is that A, if this is A, then A is equal to A transpose. And you can see that more clearly if we draw the prime diagonal of this matrix, and we can see that these two halves are just mirror images of each other. This means that the matrix is symmetric. And this is actually not just this particular example. This is going to be true always. Every single adjacency matrix of an undirected graph and an unweighted graph, even if it was weighted actually, every single adjacency matrix of an undirected graph is always going to be symmetric. And now you can figure out why. So I'm going to pause for a second, and I'm going to give you time to pause the video so that you can figure out that why this is true. So the reason why this is true, well, I'll come to it. Okay, so first we define what a symmetric matrix is. So a matrix is symmetric if A ij is equal to A ji for all I comma j. So this is the condition for a symmetric matrix. Now let's keep that aside for a second and let's focus on our adjacency matrix, or more specifically, let's focus on this. Okay, so we said that Aij is going to be 1 if node I is connected to node j. Now let's think about it. If node I is connected to node j, then obviously node j would also be connected to node I, such that here if node 1 is connected to node 2, then obviously node 2 is also connected to node 1 because they share this common edge. So that means that if Aij is equal to 1, then Aji will also be equal to 1. Okay, so let's focus on the other condition, this particular one. If Aij is equal to 0. So Aij is 0 when ith node and when the jth node are not connected. So if the ith node and the jth node is connected, the same thing happens. Jth node is also not going to be connected to the ith node. Think about this. So let's think about the other situation when Aij is equal to 0. So this happens when the ith node is not connected to the jth node. But if the ith node is not connected to the jth node, then the jth node will also not be connected to the ith node. For example, if node 1 is not connected to node 3, then obviously node 3 is also not connected to node 1. So this means that if Aij is equal to 0, Aji is also equal to 0. And you can see that since Aij can only have two values, these two statements prove that Aij will always be equal to Aji, which is the exact condition for a symmetric matrix. So the adjacency matrix is always going to be symmetric. So one of the amazing things about the adjacency matrix is that we can easily use it for directed graphs and weighted graphs. And we use almost the same definition that we defined here. So it's not that difficult to understand if you get this. So let me just get all of this out of the way. Okay, so let's change this graph a bit. So I'm going to make it a directed graph now, and 1 is going to point to 2, 2 is going to point to 3, 4 is also going to point to 3, and let's say 1 points to 4. Okay, so this is a directed graph, and we changed this definition by just a little bit, and we changed this definition by just a little bit. Aij will be equal to 1 or 0, but remember in the case of an undirected graph, Aij was 1 if node I was connected to node j. Here we will say Aij is equal to 1 if node I, I'm just going to write I because there's a lot less words. If I points to j. At 1, 2, where there was earlier a 1, we check whether 1, 2, so we check if 1 points to 2, and since this is true, there is going to be a 1 over here. But at 1 comma 4 and at 1 comma, so let's look at our matrix. Actually what I'm going to do is I'm going to create a completely new adjacency matrix so that it will be easier to understand. Okay, so it's still 4 by 4, and now we check whether node 1 is connected to itself. Hang on, let me just write these numbers. Okay, so in the case of a directed matrix, if this had a loop, then the loop would also point someplace. So this would be the example of loop. That means it's not simply going to be this edge, but the loop would also point to this node. Okay, so in this, node 1 is not connected to node 1, or node 1 does not point to itself, so the value here is going to be 0. Node 1 does point to node 2, so the value is going to be 1. Node 1 is not even connected to node 3, so the value is going to be 0. And node 1 does point to node 4, so the value here is going to be 1. Then we come to node 2. Now node 2 does not point to node 1, so the value here is going to be 0. And here we see our first difference. There's a 0 over here, but there's a 1 over here. And the reason is the definition that we changed. It's no longer if I is connected to node j, it's if I points to node j. And we can fill the rest of the matrix. Node 2 is not connected to itself or does not point to itself. So there's going to be a 0 here. Node 2 does point to node 3, so there's going to be a 1 here. Node 2 does not point to node 4, there's going to be a 0 over here. Now node 3 does not point to anything. It doesn't point to node 1, it doesn't point to node 2, it doesn't point to node 3, and it does not point to node 4. Node 4 does not point to node 1. Node 1 points to node 4, so we put 1 at 1 comma 4, but we're not going to, So here at 4 comma 1, there's going to be a 1 if node 4 points to node 1. Remember, I is equal to 4 in here and j is equal to 1, and 4 does not point to 1. So the value here is going to be 0. And 4 does not point to 2, so the value here will be 0. 4 does point to node 3, so the value here will be 1. And 4 does not point to itself, so the value here is going to be 0. And this matrix is not symmetric. And the reason is that the reason is over here. If I points to j, there's a 1, otherwise a 0. Okay, so now let's talk about weighted graphs. So remember, in weighted graphs, these edges have a weight or a cost associated to them. So I'm going to write some cost randomly, 3, 4, 2, and it's 7. Okay, and I'm also going to draw a completely new matrix, and this is going to be the matrix. Hang on, let me just draw a boundary over here, and this is going to be a new matrix. Okay, so we changed this definition. So we changed this definition when we moved from undirected to directed graph, and we're going to change it again. And for simplicity, what I'm going to do is I'm going to remove these arrows. Okay, so the definition that we're going to change, so the new definition is going to be, instead of a 1 over here, we're going to say, instead of a 1 over here, we're going to say the value here is going to be w, which is going to be the weight of that particular edge. So what that means is that when we're talking about aij, the value, if ith node and jth node are connected, then the value is going to be the weight of edge from node I to node j. So from node 1, so first is 1, 1. So node 1 is not connected to itself, so it's just a 0. Remember, the 0 did not change. There's going to be a 0 at aij if node I is not connected to node j. The only thing that changed is over this. Okay, so node 1, is node 1 connected to node 2? Yes, it is connected to node 2. And what's the weight? The weight is 7. So the value here is going to be 7. Is node 1 connected to node 3? No, it's not. So the value here is going to be 0. Is node 1 connected to node 4? Yes, it is. The value here is going to be 2. And based on this, we can fill the rest of the matrix. So node 2 is connected to node 1 and the value is going to be 7. Node 2 is not connected to itself, so this will be 0. Node 2 is connected to node 3 with weight 4, and node 2 is not connected to node 4, so the value here is going to be 0. Node 3 is not connected to node 1, this will be 0. Node 3 is connected to node 2 with weight 4. Node 3 is not connected to itself, and node 3 is connected to node 4 with weight 3. Node 4 is connected to node 1 with weight 2. Node 4 is not connected to node 2, so there will be a 0 over here. Node 4 is connected to node 3 and it's not connected to itself. Okay, so this is the matrix for an undirected graph, this is the matrix for a directed graph, and this is the matrix for this particular weighted undirected graph. Okay, so this is about adjacency matrices, and now there's one more way that we can represent this. We can represent a graph in programming. So I'm going to use the same graph 1, 2, 3 and 4. And it's actually very similar to adjacency matrix. So it's adjacency lists, and basically we maintain a list of every single node, and that list actually contains the node that it is adjacent to. So let A be all the list, and it's basically a two-dimensional array. You can think of it as a two-dimensional array. So it's very similar to our adjacency matrix. Instead of calling it a matrix, we're going to call it list of lists. So A at 1 is just the elements that node 1 is connected to. So this is 2 and 4. A at 2 is just the elements that node 2 is connected to. So that's going to be 3 and 1. A 3 is going to be 2 and 4. And A 4 is going to be 1 and 3. And that's our adjacency matrices, and this was our adjacency matrix, and this is our adjacency lists. Okay, so now let's look at the representation let's look at the implementation of a graph in a programming language. So in our example, hey everyone, let's look at the implementation of undirected graph. So I've implemented undirected graph in the programming language Java. So this is simply a class undirected graph. It has 3 instance variables, a 2-dimensional array adjacency matrix, an integer number of nodes, and a node root. So this implementation is according to the adjacency matrix and not according to the adjacency list or the lists of list that I defined earlier. So an number of nodes just contains the number of nodes that the graph has at any moment of time, and this node is actually a static class that I've defined right over here. So there's nothing complicated about this class as such. Let's skip these 2 lines and I'll come back to them later. So the element is just the value stored at the node. So earlier when we were in our earlier examples, we were drawing a graph something like this. So I'll draw a new graph. Okay, so these elements, these numbers 1, 2, 3 and 4 in this example represent the ID of the node. So each of these nodes have an ID and an element, and I'm going to write the element in red to make it clearer. So the value is 5, the value here is 6, the value here is 7, and the value here is 8. Okay, so these are the values in the nodes and these are the ID of the node. Okay, so let's get back to our implementation. Okay, so you can see that there are two distinct things, element and ID. So element is just the value stored in the node and ID is what we'll use later with the adjacency matrix. So what these two lines really do is that they define two variables, MID, which is an instance variable, and ID, which is a static variable or a class variable. That means it does not change with every instance and it is common to all instances. So when the node object is creating, what this line really does is that it assigns a unique ID to every single node object. So when we created the first node, it will be given the ID 0. So here it is, so here the minimum ID is 0. In this example, it's 1. You know what? For easier explanation, let's make this 1 as well, and you can forget about the 0. Okay, so here the when we create the first node, its MID is going to be 1 and ID would increment to 2, this static variable ID. And when we create another node, remember ID had incremented to 2 when we created the first. So when we create the second node and the constructor is called second time, the MID of the second node is going to be 2, and when we create, and ID will increment to 3. And when we create the third node, MID will be assigned the value of 3 and ID will increment to 4. Okay, so let's come to the constructor of our class, the undirected graph. So it just takes a root element and it creates a new node, and it creates a new node root, and it instantiates the adjacency matrix with min nodes. So min nodes is just this static final variable that I created to instantiate the adjacency matrix. And now you may think that what happens if we want to create a graph with 6 or 7 or even more nodes, and the answer is actually come to the answer in add node. And we also set the value of number of nodes to 1 because we added a root node right over here. So it does contain one node. Okay, so then we come to the procedure, then we come to the method add node, and it returns the node that it has added, and I'll come back to why it does that later. Okay, so it takes the int value. Remember, in our example, the value is this in red. So 5 is value, 6 is value, and 7 and 8 are values of nodes, whereas 1, 2, 3, and 4 are IDs of the node. So this check where the number of nodes plus 1 is less than adjacency matrix dot length just checks if our adjacency matrix, or the size of our adjacency matrix, which was set to minimum nodes earlier, is enough to accommodate this new node. So this block of code over here, this really if statement, if number of nodes plus 1 is less than adjacency matrix dot length, just checks whether the size of our adjacency matrix is enough to accommodate this new node that we're about to add. Okay, so we already have so the number of nodes that we have in our graph is equal to number of nodes stored in the variable number of nodes, and we're going to add one more. So we're checking if number of nodes plus 1 is less than adjacency matrix dot length. Okay, so if it is true, then we add the new node very simply. We just create a node object and pass in the value that we get over here into our node constructor, and then we just increment number of nodes by 1 and then return the node. But if this condition happens to be false, so for example, if our adjacency matrix was of the size 5 and we're going to add a 6th node, then we need to increase the size of the node, and that's what we're doing right over here in this block of code. So the first couple of steps are exactly the same. We create a new node, we increment the number of nodes, but this block of code is a very expensive procedure in terms of time. Here we're going to create a completely new adjacency matrix. So we're going to create a new adjacency matrix, and it's going to be 2 into number of nodes. So if earlier we had something like 5 nodes, and if earlier we had 5 nodes and adjacency matrix of size 5 cross 5, and we needed to add a new node, and add node method was called, then this condition would be false, and then we'll come over here and we'll create a new node, we'll increment the number of nodes, and we'll create a completely new matrix with 10 nodes, so that we can create more nodes and we don't have to call this particular procedure again and again, because this is very expensive in terms of time. And the reason is that there are these two for loops that are called number of node times each. So it's these two for loops take number of node squared steps, and that's very expensive. And then we just assign the value of adjacency matrix to the new adjacency matrix, and then we return the node. Okay, now we're almost done with our implementation of the graph, and we come to add edge. So it takes two node 2 and node from, and what it does is actually very simple. It just takes the adjacency matrix 2.mid from.mid and increments it. Oh, sorry about that. So it takes the adjacency matrix 2.mid and from.mid and increments that by 1. So if our adjacency matrix, so let's say, so I'm going to demonstrate this with the help of an example. So let's look at this graph right over here, and let's say we want to add an edge between, but let me create a completely new graph. Okay, that way this will be a lot easier. Okay, so we're going to draw this graph, and each of these nodes have a value, and I can write the value over here, and I'm going to write the value. But what you need to understand that the value for adding, when you add an edge, the value is almost irrelevant really. So but I'm going to add a value, let's say 7, 6, 4 and 1, and the numbers in yellow are the values, and the numbers in red represent the ID. Okay, so the adjacency matrix is going to be, okay, I can do that better, right? So 0, 0, 0 is going to be completely empty since there are no edges, so all of these elements are going to be 0. Okay, so let's say I want to add an edge between node 1 and node 2 right over here. Okay, so what our code, sorry about that. So what our code will actually do to add this edge is that, say 2 is equal to 1 and from is equal to 2. Okay, so 2 is equal to 1 and from is equal to 2, and now it will do adjacency matrix at 2.mid, adjacency matrix at 1, 2 is going to be set to 1. So let me just erase that. Okay, so adjacency matrix at 1, this row, so the first row, and the second column will be set. So the adjacency matrix at 1, comma 2, so that the first row and the second column will be set to 1. So I'm going to write a 1 over here. Okay, so there's a 1 over here, and if you look at the code again, then the adjacency matrix at 2, 1 will also be set to 1. Since this is an undirected graph, we will also set the value of 2, 1 to 1. Okay, so just get that out of the way. And we're going to write a 1 over here. Okay, and you can do that for any number of edges. I mean, you can, when you connect 2 and 3, then the value at 2, 3 and the value at 3, 2 will change to 1, and so on. So Next method is print adjacency matrix, which is extremely simple. It just takes the two-dimensional array and prints it. And then we have a getter, public node get root. Okay, so the isEdge method is also extremely simple. We get two nodes, node to and node from, and we check the value of the adjacency matrix at to.mid and from.mid. So if it is equal to 1, then these nodes are connected with an edge, and if it is equal to 0, then these nodes are not connected with an edge. Okay, so here we have our main method. We first create an undirected graph, a new undirected graph, and we add an edge between the root, and we add. Remember that add node actually returns a node object right over here. So that's the point of returning a node object. You can use this node object to create an edge in the graph. So and then we just print the adjacency matrix. So I hope that this code is clear, and in order to understand that, you can implement the undirected graph yourself, and you can actually think about how you can implement the directed graph, or how you can implement a weighted graph. Remember, what we do in directed and weighted graph is very similar to what we did in undirected graph. We just changed the values by a little bit over here in our adjacency matrix. And what I'm going to do is I'm also going to give you a problem, and I'll tell you the solution of this problem in the next video. Okay, so it's a very simple problem. So the problem is from this website, Hacker Earth, and it's a pretty cool website. It has a lot of problems and a lot of tutorials on graphs and sorting and searching, greedy algorithms, dynamic programming, etc. And it also has this great explanation of graphs, and it's one of the sources where I actually learned graphs, and it also has a bit of code in C++. Okay, so the problem is edge existence. Okay, that's the name of the problem, and this is the problem statement. It says you have been given an undirected graph consisting of n nodes and m edges. This graph can consist of self loops as well as multiple edges. In addition, you have also been given q queries. For each query, you shall be given two integers, a and b. You just need to find if there exists an edge between node A and node B. If yes, print yes without quotes, else print no without quotes. And it tells you an input format. So you have to solve this problem, and I actually have solved this problem, and it's actually in Python, but I think I also did it in Java. So let's see. So it works. I'll upload the solution to GitHub, but I encourage you to solve this problem on your own, and in the next video I'll explain this code, and well, good luck.